All right, so last night's homework was on page 481. You're doing numbers 23 through 33 odd. I'll talk about the first three because they were all pretty much the same type of question and what we're going to do a lot of review with today. And that's when we have one logarithm involved in our inequality. All right. So in 23, 25, 27, what we do is we take that base, raise it to whatever this number is over here. So in this case, 4 to the fourth power, 2 to the negative 2, 7 to the negative 1. And all we have to do is make sure we have that variable over here and evaluate the right-hand side. In problems like 25 and 27, remember we talked about yesterday, anytime that we have a less than sign, whether it's less than or equal to, we need to include that 0 is less than whatever my inequality is, all right? And like we talked about yesterday in class too, if it's less than or equal to, that sign stays here, but this is always less than. If they're both less than, well, then we don't have to worry about anything, okay? So those are the answers for 23, 25, and 27. Does anybody have any questions about those three examples? And then 29, 31, and 33, they were all similar since we have logs on both sides. And remember, just like with equations, with these inequalities, what we can do, make sure we have the same base, and then take each value and solve the inequality that way. For all of these problems with this inequality, they were linear. So I just have to get my constant terms to one side and my variable terms to the other. And then I just solve accordingly for X, still keeping in mind, if I ever have to divide by a negative, my inequality sign is going to flip. If I have a less than sign, again, like you see in 29 and 31, I have to make sure that I include that 0 in my answer. All right. And again, the reason for that is because if you were to take a look at the graph, all the X values approach but never touch 0. So it's never less than or equal to it. All right. Any questions about 29, 31, or 33, or anything related to last night's homework? All right. So this is where I need you to just kind of work through all of these problems for me. We're going to do just a lot of review of the same concepts so we understand this. Keep in mind that we have a mini quiz coming up next Tuesday where problems like this will be on it. So if you have any questions along the way, make sure that you ask. But let's go through each of these. So in number 1, the first thing I need to do is rewrite this as exponential. So I'll actually walk through this one on my own here. So I think to myself, well, what's the base and what's on the other side of my inequality? So I'm keeping the X here. I have my base, which is 4, raised to whatever that value is on the other side. All right. So that 3/2. Now, some of us are still having a little bit of trouble with fractional exponents, which is okay. So let's break this down a little bit. The number in the numerator, this is your power. The number in your denominator is your index. The index tells me what kind of root I'm taking. The power tells me then after I take that root, what do I have to raise that number to? All right. So as an example here, in this case, if I were to rewrite this as a radical, my index is 2, so I'm taking the square root. My power is 3. So after I take the square root, I'm raising that number to the third power. Well, what's the square root of 4? 2. And what's 2 raised to the third power? What's 2 times 2 times 2? 8. So I have X is less than 8. Is my problem over? Because it's less than, what am I forgetting? Or what do I need to include? 0, right? So 0 is less than X, which is less than 8. Like I said, anytime that you have that less than, you need to include the 0. Okay? Any questions about that first example? Pretty good. Second example. I have log base 7 of negative x plus 3 is greater than or equal to log base 7 of 6x plus 5. I have logs on both sides and they have the same base. So what should my next line be? Think about what we did yesterday in class. What would my next line be? It's greater than or equal to 6x plus 5. Good. So now I need to get my variables to one side, constant terms to the other. So I'll subtract 6x and subtract 3. So I have negative 7x is greater than or equal to 2. All right. What do I have to do on both sides here to get x by itself? What do I have to do on both sides to get x by itself? Divide by negative 7. Now, when I divide by a negative number, what happens to my inequality sign? Switches, right? So instead of being greater than or equal to, it's less than or equal to negative 2 over 7. So when I express my final answer, and this is what we talked about yesterday, not only do I have to include the 0, but I'm keeping that inequality sign the same. If it's less than or equal to, it's going to stay less than or equal to over here. So that's negative 2 over 7. Okay. Any questions about that example? Everybody good? How would I rewrite the next example so it's an exponential form? So now that we've seen this a couple problems the same time or the same way, what would I do to rewrite this in number 3? So what would be my next line? Right, so x is greater than 2 to the 4th. And what is 2 to the 4th power? 16. 2 times 2 gives me 4, times 2 gives me 8, times 2 gives me 16. This is the first time that we're seeing greater than, so we can just leave it as is. Anytime you see greater than, you don't have to worry about, including a 0 or doing anything like that. All right. Everybody understand that? Number 4, same question. How would I rewrite this so it's an exponential form? So what is it? Okay, so you can include that in the beginning, but I wouldn't start by doing that. I would just start by leaving it as x. Right, or to the 5/2 power. It is 2.5, but raising something to 2.5 or understanding how to evaluate this is going to be a little bit different. So again, I have a fractional exponent. What number is my power? What number is my index? So like, what am I taking? What root am I taking of this? The opposite. 2, right? So I'm taking the square root and I'm raising that to the 5th power. Well, again, what's the square root of 4? 2. And what's 2 to the 5th power? 32. So now, what do I need to include in my answer? The 0. So now I'll just reintroduce it. So 0 is less than x, which is less than 32. All right. Just be really careful with your fractional exponents. Remember what you're taking the root of, what your base is, or not what your base is, excuse me, what your power is, and then evaluate from there. Like I said, always start by taking the root, like we just did, and then raising it to that exponent. All right. Any questions about that example? All right, last 2 for this little bit of review, and then we'll do an application problem, and then we'll just move on from there, okay? So how would I rewrite this now so it's an exponential form? x is less than or equal to 27 to the 2/3. Good. Same type of problem as the last one that we just did. What root am I taking of 27? Or what number goes on the outside as my index?
3.
3. What's my power? Well, the only one that's left over, right? 2. What is the cube root of 27?
Is it 9? I think.
So not 9. That would be 27 divided by 3. So you're looking for a number that you can multiply by itself 3 times to get 27. Does anybody know? 3. And then I square that, and what's 3 squared? 9, right? Is my problem over? No, because what else do I need to include? Because it's less than 0. So 0 is less than x, which is then less than or equal to 9. All right. Any questions about number 5? All right, last one on this page. I have x is greater than 5 squared. What's 5 squared? 25. So I just have x is greater than 25 for my final answer. All right. Any questions about this idea? Anything from this first page? All right. So expect to see a problem or two like that on the mini quiz on Tuesday. So if you have any questions about it, make sure that you reach out. I wanted to take some time today also to kind of just introduce some applications of logarithms. So where you might see, an example of this out in the real world. Because yes, it's enough to be able to solve these or evaluate them, whatever, to be able to take tests and stuff like that. But also we want to understand the application of this. All right. So I found this is actually in your textbook. I thought it was kind of an interesting problem, talks about some different stuff, allows us to kind of revisit some older ideas with logarithms. So it says the first key on a piano keyboard corresponds to a pitch with a frequency of 27.5 cycles per second. All right, so we're talking about the frequency of sound as it relates to a piano. With every key after that going up and down this piano, the pitch multiplies by some constant. All right, and the formula to represent that is as follows. So it's pretty involved, right? I have 1 plus 12 log base 2 of f divided by 27.5. There's a lot of stuff going on there, right? So essentially how we could break this down is the number of keys is n and the frequency is f. So if we plug in a frequency, if we know a frequency or we understand what key we're dealing with, we'll be able to kind of use this equation to help us solve for either of those two variables, all right? So the first question that we are given, and they're going to be relatively similar between parts A and B, says a note has a frequency of 220 cycles per second. All right. So it gives us the frequency, it gives us F. So we're going to take 220 and plug it in for F, and they're going to try and help us solve for N. So how many notes up on this piano that we are? Does anybody play the piano by any chance? Anybody ever tried to play the piano?
I have. I have a piano at home.
Nice. You play it at all, or you just have one?
And I just have it. My brother like he has music class, so he plays it.
That's awesome. Just bang on the keys. I picked it up a little bit myself, but nothing too much. Initially, you say you played it?
Well, not old school, but kind of made us learn a bunch of different instruments. So they taught us guitar, bass, piano, drums.
What? That's awesome.
And vocals, I believe.
Is this a school of rock?
No, it was just schooling. So they made us learn a bunch of things. It was a charter school. And so they made us learn a bunch of things. And so we did learn a bit of piano. It wasn't super in depth, just
right.
Basics. But I was mainly a bass. I mainly started with bass. So I never really into that from non-guitar.
That's awesome.
But yeah. It made us
I love that. That's incredible. Very, very cool. Well, there's math behind playing the piano, so making connections. All right, so here's what we're gonna do. We're gonna take this number, the 220, and we're gonna plug this in for F, and we're gonna find out what note on this piano we are at. All right. So when we plug this in, we're going to be solving for n, right? Because notice that's the only variable that we have left over. So I'll pull up my calculator here so we can kind of all follow along. If I do 220 divided by 27.5, I get 8. All right. So this next line is going to be 1 plus 12 log base 2 of 8. Okay. So what we're going to do from this point is just evaluate this piece right here. I'm actually going to box this off so we understand kind of like the order of operations of what we need to do. You probably heard that term before. We want to deal with this function to start. All right. So what we're going to do is evaluate log base 2 of 8 equals x. And the way that we do this and what we saw earlier on in sections, in chapter 7 was the ability to rewrite this as an exponential and then solve this equation. All right. In fact, this is something that we did earlier on in section 7.4. So if I were to rewrite this as an exponential, what would the next line be? So what's my base? What am I setting my equation equal to? To what? I just can't hear what you're saying. I'm sorry. Not to the 8th, to the x power equals 8. All right, so just rearranging it, so now it's an exponential equation. Well, 2 raised to what power gives me 8? The 3rd, right? And the way that we would solve this, I'm just gonna skip that step for now since we've done it already. But remember, we would get common bases, set the exponents equal to each other. So right now I have x is equal to 3. All right. So when I evaluate this entire thing right here, the value is just 3. So I'm going to take 3 and plug it in wherever I saw this entire function. So I have 1 plus 12 times 3. What's 12 times 3? $36. And what's 36 plus 1? 37. So we just use the logarithmic function given the frequency of a key to find out specifically what key on the piano that was. Pretty interesting. How many keys are on a piano? Does anybody know? A lot. Is that what you said? All of them? All the numbers? What's that? 108? Look it up. You guys are all texting anyway. $88. So we found the 37th key out of 88, somewhere towards the middle there. Still pretty low. All right, let's do another one. Very similar problem, except now we're talking about 880 cycles per sound. So we're going to use the same equation. But just plug in 880 wherever we see F, because that's the frequency. All right. So 880 divided by 27.5 gives me 32. So now my next line is going to be 12 times log base 2 of 32. All right. What's going on?
Can we get a Boston nurse?
Yeah. All good. All right, so now we're gonna plug in 32. So just like what we did in the last example, we're just gonna evaluate this piece right here, this log equation, and then plug that value back in. All right, so we'll evaluate this. I have log base 2 of 32 equals x. So how would I rewrite that in exponential form? 2 to the power of x equals 32. So what does x equal? 5. 2 to the 4th, 16. So now what I'll do is take that 5 just like before and plug it back into my equation where I saw this entire logarithmic function. All right. So I have 1 plus 12 times 5. What's 12 times 5? 60. And then I add 1. So the note that I'm at here is the 61st note. All right. Pretty cool. Any questions about either of those two examples? So just showing, how we could relate this to something, out in our day-to-day lives. All right. Everybody good there? Any questions about either of those two examples? All right. Let's just do one more problem. So this one's a little bit different. You might find it maybe a little bit more approachable as well. So it says, excuse me, the magnitude of an earthquake is measured on a logarithmic scale, and it's called the Richter scale. This is actually a true thing, very real. The magnitude m of any earthquake is given by the equation log base 10 of x, where x is the amplitude of the wave and its ground motion. All right. So this might be related to, like environmental science or something like that. If you wanted to pursue that, you might be dealing with logarithmic equations. So it says, how many times greater is the amplitude caused by an earthquake with a Richter scale rating of 8 as an aftershock with a Richter scale rating of 5? So we're just comparing two different types of earthquakes and how much greater the amplitude would be depending on its scale. All right. So the way that we would do this, we're going to have two different equations. We'll have the same thing, but we're going to compare each of them. All right. So I start with my original equation. And on this left-hand side, what I'm going to do is take 8, which is my magnitude, which is m, and plug it in for that variable. So I have 8 equals log base 10 of x. On the right-hand side, I'll have 5 equals log base 10 of x. Okay. Now we need to evaluate this. So we're going to do the same thing that we did before when we were solving our logarithmic equations, and that is to rewrite this so it's an exponential form. So how would I rewrite this? And we'll just deal with one equation at a time. Right, 10 to the 8th power equals x. Ten to the 8th power just means it's 8 zeros with a 1 in front of it. So it's 100 million. Okay. So it's 100 million. Hey. Not yet. I'm going to email them soon. Guess what we're doing right now? Logarithm equations for earthquake.
Yeah, because it's a logarithmic scale. It gets way more as you go.
Richter scale.
Richter scale, yeah.
Everybody know this is Sparty?
Take AP Environmental.
AP Environmental Science.
Yeah, I have her.
Nice. She's in here right now. She's saying hello.
Hey, Ms. Buff.
Hey, that Nick Barges. No.
Nope, it's me.
Well, my screen's shared, so I think it. Who was that? Joel? Joel.
Yep.
Joel. Is
Yeah.
it Joel? I've called him
Yeah.
Joel all year. Joel, you should have told me that wasn't your name. I called you Joel all year and it's Joel.
It don't matter. I'm fine with it.
Man, that was a really big, mature thing for you to do, so I thank you. See you later, Superman. Not calling you anything else but Superman. Vince and Zortho from Ghostbusters.
Nice. I don't have fun nicknames for you guys, but all right. So it's 100 million. Okay. What about this right-hand side here? How would I rewrite that so it's an exponential? 10 to the fifth power equals x. 10 to the fifth, same thing. So it's 1, 5 zeros that follow it. So that's 100,000.
It's 10 5 zeros or
1, 5 zeros. See? Okay. So now what we're gonna do, it says compare those. So how much greater is 100 million to 100,000? All right. And what you could do, and hopefully somebody in an earlier class told you how to do this without having to use a calculator. You just cross zeros out. You understand that rule if you're ever dividing something by tens? No, you don't. Don't lie. So you cross the zeros. So it's 1,000 over 1. So it's 1,000 times greater. All right. God. And now you know, anytime you hear someone talking about earthquakes, you're like, oh, Richter scale of 8, Richter scale of 5. I know that's 1,000 times greater. Don't ask me how I know. I just do.
I'm gonna bring that up every time I hear that.
All the time. You can go home and tell somebody that.
I know I will.
Hey. And you could do it with anyone. You could do it with a Richter scale of 10 and 2. Figure out how much greater that is. All right, a little bit of application, a little bit of fun, in my opinion. Any questions about anything that we covered today? Everybody good? All right, let's just chat real quick about some stuff that's upcoming. So there is no homework for the weekend. Wanted to kind of just give you guys a little bit of an easier Friday. One thing related to this class in particular, as well as my second period, so my last period, I have to take the beginning half of the day off on Monday. So I will not be here, but you do have review to do for our mini quiz on Tuesday. So we've covered everything. We've reviewed everything up until this point. So it's not like you're learning anything new, just a matter of, going through and asking any questions. If you have any issues with any of that, make sure that you reach out. There will be an assignment related to it, and I'll kind of send out a message to both class periods regarding that. Okay. Although we did just talk about it in class as well. Other than that, on Monday, we'll do the review. Tuesday is the mini quiz. Wednesday, we're just going to kind of conference and see if anybody has any issues about grades and stuff like that. It's the virtual Wednesday anyway, so it's going to be a pretty light day. And then Thursday and Friday next week, we're going to do some more like finance type stuff. So remember how we did compound interest? We'll do something a little bit different to kind of just relate to some interesting stuff. I have a little bit of an activity on Friday. And then that brings us to the last week of school. All right. So just to kind of give you a heads up of what to expect for the next week or so from here on out. All right. Any questions about that or anything related to class?
What? I feel like we should be out right now.
All right. Well, with that being said, those of you that are at home, you can go ahead and sign off. Those of you that are here, just work on something quietly for the next few minutes or so before the bell rings. All right. Those of you that are at home, take care. Have a great weekend.
Have a good one.
See you later.